titanium based alloys, alpha, beta, alpha plus beta, and we looked at the philosophy behind these alloys, that which alloy should be used for what kind of applications, why alpha works better for high temperature strength when compared to beta, and what are the advantages of beta as far as formability is concerned when compared to alpha. We looked at all of them. Today let us try to look at another aspect of the alpha beta alloys, and then go to the other type of titanium based alloys, which are the shape memory alloys. So when we talk about the mechanical properties of alloys particularly, we come across three types of properties: the strength, the ductility, and the toughness. And for most of the common I would say consciences, people usually consider ductility and toughness to be almost synonymous to each other. But we know that they are not like that. It's possible that material can be highly ductile but at the same time not tough, and at the same time material can be highly tough but at the same time not ductile, because the two are, though they are related to some kind of deformability, but their concepts are entirely different. The ductility is basically the amount of deformation that you can give into a material before it fails. That's what is ductility. Percentage elongation we talk about, and percentage reduction in area. So that is ductility. That means how much of deformation you can, how easily a material can be deformed. That is a measure of the ductility. But when you talk of toughness, toughness is basically the resistance of a material for the crack propagation. Whenever you have a crack initiated in a material, and if the crack propagation is made more difficult, then we say the material is more tough. In fact, quantitatively measuring, we take the area under the stress strain diagram. If you have the stress strain diagram like this, the stress and the strain, this area under this stress strain diagram is nothing but the toughness, isn't it? That's how we measure. And percentage elongation is the total elongation that you have before the fracture has occurred. So that's the percentage elongation. So this is as far as quantitative is concerned, but qualitatively we know that the two concepts are different. One is about deformability, another is about the resistance of the material for the crack propagation. So that's why we say a brittle material has very poor toughness, because a crack can very fast it can propagate in the material, and then finally the material will break. Whereas a material, for example, if you take even martinsite we say is very tough under many conditions. In many alloys, martinsite is very tough, though it may not be very ductile. So what is this? What controls this? How to control the microstructure to control these two properties, that the ductility and the toughness, and finally the strength also, and to ultimately get a proper combination or an optimum combination of all these three. This is one effort which in titanium based alloys people have successfully achieved, and that is trying to control the microstructure of alpha. We know that alpha is a low temperature microstructure, low temperature phase, and beta is a high temperature phase. So if you take a high temperature beta and try to cool it, what do you get from there? When you take a beta which is at high temperature and start cooling this beta, alpha should precipitate out of it, isn't it? So depending on the composition, the volume fraction of the alpha is going to be different. So usually alpha has to precipitate, unless you are talking of those alloys where a large amount of beta stabilizers have been added in such a way that beta gets stabilized even at room temperature. Okay? So if you do not consider such type of alloys, all those alloys where you have a alpha plus beta possible at room temperature, when you take it to high temperature it is beta, and when you start cooling it, it gives alpha. But now the question is, depending on the morphology of this alpha inside the beta, the properties are going to be different. If you have a microstructure of beta in which you have alpha as this kind of spherical particles, let's say, or some kind of more or less spheroidal particles, in this kind of a material, if you look at the mechanical properties, you will have a good strength because it is the two-phase mixture. Whenever you have a two-phase mixture, you get good strength. This is known to us. And then if you look at the ductility aspect of it, this material will have very good ductility. It will have good strength, good ductility. Why good ductility? Because the particles are spherical, and because the particles are spherical, the material can be easily deformed. There is no triaxial state of stress coming into picture. This is what we have seen in case of even spheroidal graphite iron, or when we take high carbon steels, the hypereutectoid steels, and spheroid is the cementite. There also we see that we can improve the ductility, isn't it? So because whenever you have a spherical particles, you will not have a triaxial state of stress at the corners. The particles, if the particles present in the material are needle shaped or acicular, that is when you will see at the tip of each of these particles you will have a stress concentration taking place, and that is what is going to lead for the crack initiation and finally the fracture of the material. So you have to avoid stress concentrations, and the best way to avoid stress concentrations in a two-phase material is to have spherical particles, isn't it? So that's why this material gives you a good ductility, but it will not give you a good toughness. Basically because if a crack is initiated inside the material, let us imagine a crack is initiated here, it can easily propagate because these are all mostly spherical particles. Spherical particles do not really offer much resistance for the crack propagation. But if you have acicular type of particles, particularly which are randomly oriented, that means if you have a microstructure, let's look at another type of microstructure where you have this type of acicular particles in an in a beta matrix. The matrix is beta and these particles are alpha. Again, here also is the same. The particles are alpha and the matrix is beta. If you look at this kind of a microstructure, this microstructure will have like the first microstructure, it will have good strength, no doubt, and it will have good toughness, but it will have poor ductility. The ductility of this alloy will be very poor. So as a result, we can see that these two different microstructures, one is having a good ductility, another is having good toughness, and the two do not have, for example, the first microstructure do not have a good toughness and the second microstructure will not have a good ductility. So this is something which people know quite before, and in titanium based alloys they try to see how we can achieve a combination of these two. The easy way to say is try to have both type of particles. The question is how to have it. So what people try to do is, we know that the morphology of the second phase depends on the way we do the heat treatment, and particularly it depends on the temperature at which the precipitate comes out. Usually if you have a high temperature single phase such as a beta, and if it is cooled very fast to a low temperature, and if the precipitation starts at a low temperature, at low temperature the precipitation usually is a Widman-Staten type, acicular type of precipitates take place. The reason is at low temperature the precipitates, because the diffusivity is very low, okay, the precipitates that come out will be those which can be coherent with the matter. So usually acicular type, disc type or plate type or needle type precipitates will come, which can have some coherency or at least a semi coherent interfaces with the matrix. This usually occurs at much low temperatures. So, as a result, if we can have the precipitation occurring at much low temperatures, we are assured to get this kind of acicular precipitates. And if the precipitation occurs at temperatures closer to the transformation temperature, if the delta T is very small, the precipitation usually is by more or less spherical type of precipitates, which are called grain boundary allotriomorphs. If you look at the growth rate, of coherent versus semi-coherent, coherent versus incoherent precipitates, at low temperature, if you are talking of delta T increasing, that means this here high delta T means low temperature, low delta T means high temperature. At very low temperatures or high delta T, the growth rate of coherent precipitates is much faster. Okay, because the precipitation of incoherent precipitates does not occur at high undercoolings. So, whereas when you come to high temperatures, at high temperatures the ratio between these more or less reaches equivalent to 1. So, if you try to plot, you will get this kind of a situation. So, the tendency for the formation of coherent precipitates is much higher at high undercoolings, and when you come to low undercoolings, which are very close to the transformation temperature, you have a greater tendency for the formation of incoherent grain boundary allotriomorphs. That means the precipitation occurs near the grain boundaries, not within the grains, and then the growth occurs into the grains, and then the morphology of the precipitates will be more or less spherical, not really acicular. Okay, and they more or less grow in a symmetric fashion into the grain boundary in a more or less a spherical kind of a situation. So, as a result, one can have a two-stage precipitation process where one can achieve both these type of microstructures. That means you first heat it to a beta single phase region, then cool it suddenly to a temperature just below the transformation temperature, and then hold it for some time, so that you have grain boundary allotriomorphs coming out, and then before the precipitation is complete, you take out the sample from that furnace and quench it to another furnace, a low temperature furnace, and hold it again there for some time, so that the remaining precipitates come out as a Widmanstatten type of acicular precipitates. So, this is a two-stage precipitation process or two-stage annealing process people have adopted in the titanium based alloys to give you a combination of both, that you have some precipitates which are of this type and some precipitates which are of this type. If you have a combination of these two types, then you achieve what you really are looking for: the high strength, the high ductility, and high toughness. A good combination, I would say. I would not say all of them are very high, but an optimum combination of all the three. Under these circumstances, it will not be a situation that the toughness is very low or the ductility is very low. They will be reasonably high, when compared to any of the two microstructures that I have shown you before. And in this way, in alpha beta alloys, people have been able to get very good combination of properties, and which are being used nowadays for high temperature applications at least about 550 degrees centigrade or so. For particularly the airframe type of applications where you need some formability and high strength. So these type of alloys definitely are not useful for the high temperature jet engine type of applications, because in jet engine type of application you need more or less single phase alpha, because if you have a two phase microstructure, then unless you have the second phase being very stable, such as a dispersoids, we have seen in a nickel based superalloys, for example, yttria is added, which does not dissolve back into the matrix. So for high temperature applications, you really need precipitates which do not dissolve back into the matrix at high temperature. If they start dissolving back into the matrix, obviously you cannot use that alloy for a high temperature application. For example, here if you take the alpha beta alloy and put it at around 900 degrees centigrade for a high temperature jet engine, then this alpha which has come out of beta during the precipitation obviously will dissolve back into the beta, and you get into a beta type of alloy. So we don't use alpha beta type of alloys or beta type of alloys for high temperature applications. Beta type of alloys, why we don't use, we have talked about it in the last class, because beta is BCC. So we never use a BCC structure for a high temperature application. So that's why if you want high temperature mechanical strength, good creep resistance for the jet engine type of applications, we need to go for alpha type of alloys. For structural applications, we go for alpha beta type of alloys. Okay, so keep that in mind. Similarly, beta alloys are also useful for structural applications, but single phase beta alloys, because they cannot be heat treatable, so their advantages are limited when compared to alpha beta alloys. Alpha beta alloys can be really heat treated and one can achieve much better properties. The other major titanium based alloys are what are called shape memory alloys. Though there are also other alloys other than titanium based alloys which are used for shape memory effect, the most popular alloy is a titanium nickel alloy. People call it as nitinol. So that's from where most of the work on the shape memory effect has come into picture. So let's try to see what are these shape memory alloys. First of all, why do we call them as shape memory? What is the basic requirements for a particular alloy to show a shape memory effect, and what kind of alloys show this kind of shape memory effect? Let us try to see that. What is a shape memory effect? First of all, a shape memory effect is basically that where the sample remembers its shape which was under a certain condition when it has been taken to some other processing condition and brought back to the original condition. For example, you take a titanium nickel alloy, 50-50 alloy. 50-50 alloy has what kind of a structure? Do you know? TINI. It's a BCC B2 type of ordered compound. It's a B2 ordered compound. So if you take a B2 ordered compound, it has a martensitic transformation. It undergoes a martensitic transformation at low temperature. Okay, TINI is one of, there are so many alloys which show martensitic transformation. We know even steels show martensitic transformation. So similarly, TINI also shows martensitic transformation, but the only difference is this particular alloy shows this shape memory effect which the normal steels do not show. We will also try to understand why the normal steels do not show it. So let's try to see what happens in this alloy. You take the austenite in the TINI, high temperature phase is usually we refer to as austenite, though it is nothing to do with the steel austenite, but nowadays most of wherever a martensitic transformation takes place, all those alloys, the high temperature phase is usually called as austenite, okay, though it is not related to iron carbon austenite. So that austenite, if you cool it to below the MS temperature, that means where the martensite starts forming, and bring it to the martensitic condition. The martensite here is a rhombohedron type of martensite, rhombohedron structure, and this martensite is a real deformable type of a martensite. It is not very brittle like in steels, it is not very brittle, but this particular martensite is deformable. So if you deform this martensite by a small amount, let us say you take a rod like this in the austenitic condition, bring it to below the MS temperature and then deform it, bend it, let us say, and then once you have bent it below the MS temperature, bring it back above the AS temperature, austenitic start temperature. Once you come into the austenitic region, the bent structure comes back to the normal position. That means the alloy has somehow remembered what was its shape in the austenitic condition, and it tried to remember that shape and come back to that particular shape. Otherwise, usually when you bend a sample, okay, just by when you heat it, it does not come back to the same position, isn't it? So this is a particular property of a special class of materials which are called shape memory alloys, and nowadays people refer to them as smart materials. This is a term which is used for most of the materials which have some property which can be kind of tailored and used for some advantage. For example, piezoelectric materials, these are also called as smart materials. Piezoelectric materials means if you provide some electricity, okay, it deforms, and if you deform it, it gives you some electricity, okay. So all these kind of materials where some physical properties are affected, some physical or mechanical properties are affected because of some changes which are taking place inside the material, which can be used for to an advantage. How we use it to an advantage, we will try to see it in terms of some applications of these shape memory alloys. And so this is particularly the effect that you see. And why does this occur? Under what conditions it occurs? Does every alloy which undergoes a martensite show this? No. First thing is, for example, steels, you take it. Steels, if you take a martensite, take an austenite, bring it to martensite and start heating the martensite. What happens to the martensite? It gets tempered. It transforms to a tempered martensite, and it does not transform to an austenite. So the first and foremost criterion for an alloy to show you the shape memory effect is that it has to be a reversible transformation. The transformation has to be reversible. That means I take an austenite, bring it to a martensite and heat it back. I should get back the austenite without any intermediate step. See, even in steels, if you ultimately go to above A3, it will come back to austenite. Even in a tempered martensite, if you say, sir, no, it is also reversible because it comes back. If I heat the martensite up to A3 temperature, it will come back to austenite. There is no solution. Okay, but before it transforms to the austenite, it has already transformed to an alpha plus either epsilon type of a microstructure or alpha plus cementite type of a microstructure, and finally that alpha plus cementite is what is transforming into the austenite. So this is not called as an reversible transformation. So reversible transformation is that where there are no intermediate products coming out. Okay, so this is first and foremost criterion, that it has to be a reversible transformation. Second thing is that this martensite has to be a thermoelastic type of a martensite. What is the thermoelastic martensite? Thermoelastic martensite means a martensite where when an austenite transforms to martensite, the strains that are involved during this transformation, because we know whenever a martensite transformation occurs, it is a shear transformation, isn't it? Whenever there is a shear, there is some strain involved. These are called transformation strains. Okay? So, austenite to martensite transformation always involves some strain, and if this strain is very small in nature, not more than about 8%, usually people have seen that shape memory effect always occurs if the transformation strains are not too large. Why they should not be too large? Because if they are too large, when you try to heat the sample, the strains are not completely recovered. The strain has to be small enough so that when you heat it, the strain is recovered, and that is a crucial aspect of thermoelasticity. So, thermoelastic martensite is that where these transformation strains are elastic in nature, they do not bring in really a major plastic deformation, and these strains can be recovered back when you heat them, and that is a typical nature of a thermoelastic martensite. And the third point should be the strains should not be too large. In iron carbon alloys, the strains are too large. This is one of the major problems. For example, in case of iron nickel alloys, if you look at the difference between MS and what is called AF or AS temperature. Okay, so here we have 4 different temperatures we refer to as. Okay, the MS temperature where the martensite starts forming, the MF temperature where the martensite finishes formation. Then when you are heating this martensite, there is one temperature called AS and another temperature called AF. Austenite start, austenite finish, because all these transformations, the AS and AF, these are all basically thermally induced transformations. So as a result, as a function of temperature, the transformation occurs, and it starts at a particular temperature and complete transformation occurs beyond a particular temperature. So there are 4 temperatures that are involved. So if you look at the difference between MS and AS, this difference is very large in iron nickel alloys. The reason is because the total amount of strain that is generated in iron nickel alloys is very large. So when you try to heat it, you have to heat it to a large temperature range before all these strains are recovered and transformed back to the austenite. So that's why usually iron nickel alloys do not show much of a shape memory effect, whereas the titanium nickel, the difference in the temperature is only about 10 degrees. Okay, so if you look at the various alloys which give you the shape memory effect, there are a range of alloys, mostly non-ferrous. If you look at it, most of the ferrous type of alloys, iron nickel to some extent shows, but it, as I told you, the difference in the temperature is too large for many practical applications. So because of which, so you can see the titanium nickel is one of the very crucial examples. The composition range I have given here 49 to 51%, and the transformation is basically B2 to a rhombohedral type of structure, and the difference between these two temperatures is about 10 Kelvin. The MS temperature is about 298 and AF temperature is about 308 Kelvin. So it's about just 10 degrees. But what is important is this is quite sensitive to temperature. If you look at the titanium nickel, if you change the composition, the MS temperature drastically changes. If you take about 55% nickel, the MS temperature is about 320 Kelvin. If you take about 58%, just increase the concentration by 3% nickel, you will see the MS temperature falls to about 220, almost 100 degrees. So these temperatures are very sensitive to the composition of the alloy. So one has to consider the composition very carefully. And a number of non-ferrous other non-ferrous alloys which give you this type of shape memory effect. Gold cadmium is one, where B2 to hexagonal type of transformation in the range of 46% to 50, and copper zinc alloys where the beta transforms, the beta brass, you know that it is a B2 structure. B2 structure transforms to rhombohedron, and copper zinc aluminum is the most commonly used shape memory alloy. Okay. Copper zinc anyway shows, I told you, but if you put a small amount of either silicon or tin or aluminum or gallium, it also shows you a good shape memory effect. And nickel aluminum, the NiAl, and nickel silicon, NiSi. So there are a number of these alloys, and what is important to note is most of these alloys, the shape memory effect is observed at intermetallic compositions. Most of these phases which transform to martensitic transformation and give you the shape memory effect are all mostly intermetallics and ordered intermetallics. And these ordered intermetallics will undergo these thermoelastic martensitic transformation, and which will give you this kind of shape memory effect. And this MS temperature, as I told you, is a function of composition in many of the alloys. Just if you look at the copper zinc based alloys, if you look at the MS temperature is a strong function of the composition, as is shown here. MS is given by 3280 minus 80 into zinc minus 175 into tin and minus 120 into silicon. So you can see clearly how strongly each of these elements, these are all atomic percent, whatever percentages of various elements shown here, these are all atomic percent. So you can see each element almost very strongly affects this MS temperature, and MS temperature is very crucial to know what is the temperature below which this transformation occurs. Okay, and if you look at the applications are very wide. We have engineering type of applications, we have biomedical applications. I will also try to show you some pictures that I have collected. In the case of engineering applications, the most important applications are where you need couplings and actuators, particularly in sensors. We will try to see some of them. And in biomedical applications, particularly whenever you have the fracture in the bones, so the bone plates or teeth braces, even for example artificial muscles, when you have an artificial heart installed in the body. So the artificial muscles can also be shape memory alloys, where you at the body temperature they can contract and expand. So whenever there is a blood pressure, so based on the blood pressure, one can have expansion and contraction, and that can lead to the typical blood flow in these veins of these artificial hearts. So one can use them here. Let's try to see some of these here. Okay, what is this thermoelastic martensite? If you look at the austenite in most of these things is cubic in nature, the B2 type of structure, and the B2, if it transforms to the martensite, thermoelastic martensite, the strains that are present during this transformation are absorbed into this martensite in terms of a lot of twins. You get lot of twinning inside the martensite where the strain is stored, and if you deform this martensite at temperatures below the MS temperature, the deformation leads to a shear type of deformation and deforms this martensite, and when you heat it back, you get back this particular structure. And how does this occur? A schematic picture is shown here, where the austenite at high temperature is brought to the martensite by cooling, and during this transformation there is a lot of finning that takes place inside the martensite, and when you deform this at temperatures below the MS temperature, this martensite gets deformed, and this deformed martensite, if you start heating it, you get back this austenite, and whatever deformation that you have given is lost and you get back this original shape, and that is what we call it as a shape memory effect. And if you look at the other way, you see here different temperatures are shown, the MS temperature, MF temperature, MS temperature, AS temperature and AF temperature. The 4 different temperatures are shown, and these temperatures are a function of the pressure. You all know that whenever we pressurize, the transformation temperature changes. What is this kind of principle called? We have talked about it in thermodynamics. The Clausius-Clapeyron equation. Okay. So Clausius-Clapeyron equation. So from that you can see when you load a material, okay, depending on the type of structure, so the transformation temperature changes. So here the transformation temperature increases with increasing load. So if you look at the high temperature austenite, it is shown in the red color because the temperature is high. So this austenite, if you bring it back to the martensite by cooling it down, this martensite, if it is deformed and then heated back, you get back the original shape of martensite, of the original austenite, and retains whatever shape that you have in the original condition. In fact, I had a few video clippings. I wanted to bring that, but somehow they were not working on this PowerPoint. Maybe some other time I will show you those clippings. So the basic structure is shown here. You can see it is the cubic B2 type of structure, titanium occupying all the body corners, nickel occupying the body center. That is a typical austenitic structure, B2 type of structure, and when you change it to martensite, it becomes the rhombohedron. Okay. So this is the typical rhombohedron type of structure where you have the atoms occupying again the similar positions, but the structure changes from the BCC type to rhombohedron type, and a number of applications are given here where we use the shape memory effect. A simple starting from a simple coffee pots to a space shuttle, thermostats and hydraulic fittings, different applications where we use this shape memory effect. The other most important concept here, which is very similar to the shape memory effect, is called pseudo elasticity. In a shape memory effect, what we do, we take a high temperature structure, bring it to the room temperature, deform it at bring it to below the MS temperature. I do not call it room temperature because we do not know where is the MS, depends on the composition. So we bring it to below the MS temperature, deform it in the martensitic state, and then heat it back, and we get the austenite back and the original shape back. Whereas in a pseudo elasticity, what we do is we do not change the temperature. We keep it in the temperature above the AF where it is completely austenite and start deforming the alloy. When you deform the alloy, increase the load at a fixed temperature, the temperature is above the MF, and when you start deforming it, the moment you start deforming it, it becomes martensite because deformation induced martensite comes into picture, and once you come to a martensite completely either above the MS or completely above the MF depending on your interest, okay, and then release the load. Once you release the load, then the shape comes back to the original position. So here there is no temperature involved, it is only the deformation it is involved. So but the shape comes back to the original position basically because the strains that are involved are elastic strains and deformation induced strains. And these deformation induced strains, the moment you release the strain, it comes back because the amount of strain is very small. Similar thing does not occur in the kind of steels. For example, in steels you take an austenite and deform the austenite, and we see that we also see deformation induced martinsite formation, but then you do, when you release the strains, it does not come back to the austenite because the amount of strains that are involved are very large in steels, basically because of the carbon atoms which are present there, which occupy the octahedral positions. So because of which they prevent the martinsite to come back to the austenite very easily. Whereas here the amount of strain that is involved during the transformation is small, because of which if you heat it, if you deform it to the martensitic condition and then release the strain, it comes back. So you can see vertically in the loading direction we go up and then release the strain, it comes back to the original position. So this concept also is used in a number of examples, such as, for example, eyeglass frames, where this kind of thermoelastic martensite pseudo-elasticity is used, cellular phone antenna and orthopedic implants, orthodontal implants and other medical tools. And some of the examples are shown here. This is one example where we use these materials in aircraft applications, where whenever you have an aircraft, the actual maneuvering of the aircraft, whenever you want to turn it or lower it or take it to higher heights, it's all done with these wings. Here you have some kind of fins which keep on moving, and this movement is what gives you the drag and the lift. So based on that, you can have the raising or lowering of the aircraft can easily occur, particularly during landing or during takeoff. These are very crucial parts, and this movement of this is usually done by hydraulics. Okay, you have a hydraulic cylinders which are used to either pull it up, the fins are raised up or brought down, is done usually by the hydraulics, and you have heavy hydraulic pumps inside the aircraft because of that. So nowadays people want to use this kind of shape memory alloy wires, where the shape memory effect can lead to either movement of these fins in a downward direction or upward direction depending on the loads. For example, depending on the pseudo-elastic nature of it, whenever you have a load, the moment you give an electrical signal here, okay, and that electrical signal transmits to that, and then that induces some kind of a pressure on the shape memory alloy, then immediately it transforms to either a martensite, or if it is already in the martensitic condition, it transforms back to the austenitic condition. So like that, by change of the transformation from austenite to martensite, it is just by a phase transformation we can have this whole fins, okay, moving either upward or downward. This is one of the application. Another most crucial application is wherever the bones are broken. Earlier also people used to put some plates like this, particularly cobalt based alloys or titanium based alloys. Titanium based alloys are very popular for medical application, particularly because of their high corrosion resistance. Titanium based alloys have very good corrosion resistance and good biocompatibility. So as a result, titanium based alloys are used in all these applications. But what is the speciality of the shape memory alloys is that, so the application here is simple, that let us say the bone is broken, you bring both the bones together, put them together and put this kind of plate there which join both of them. You drill 2 holes in these 2 bones and put a screw so that that plate is held on these 2 bones, one on top, one on the bottom. The bottom one is not seen here. So you put one at the top and one at the bottom, and then you hold it there for some time, let us say 2 months or so. So during this period the bone grows, and once these two get joined, then you do another X-ray and find out that both of them are joined and there is no dislocation there, there is no crack there, and then you can remove those plates. This is the usual technique which everybody employs till the shape memory alloys have been discovered. But once the shape memory alloys have been discovered, the advantage here is that you can take the shape memory alloy which is austenite at the body temperature, and if you take this austenite to below the MS, which is let us say a much lower temperature, let us say 10 degree or so. What is our body temperature? About 37 degrees centigrade. Okay. So you take the sample alloy to a very low temperatures at the where the transformation occurs to the martensite, and then you put it into this bone. You do a surgery and then put it there, and the moment this comes back to the austenitic temperature, then it shrinks. The martensite, once it goes, martensite is a when it goes to austenite, austenite is a structure which is more close packed than the martensite, so there is a shrink. Okay. So once it shrinks, what it happens is it pulls both the bones together and then holds them together. So there is a kind of a compressive strain. Okay. So if you think of this plate, the plate shrinks. When the plate shrinks, okay, the two bones are brought together, so that they are held together very closely, so that this what is called curing occurs much faster. So that's one of the advantages where people have been using the shape memory alloys to a large extent, and nowadays it's very common to use the shape memory alloys. The only factor that one has to consider is what is the biocompatibility of these alloys. A lot of work is being done where people, at the same time, one cannot really do experiments on the people, so they try to do experiments on the animals, or for example nowadays there are synthetic liquids available which are, for example, what we call the body fluids. So whenever the shape memory alloy is kept inside your body, it experiences a lot of body fluids, isn't it? So these body fluids, whatever is their pH value and whatever is their concentration, these kind of things have been simulated outside by chemicals, and then in some such chemicals people try to keep these shape memory alloys for years together and check whether it gets any corroded or not, and then try to see whether there is any stress corrosion, cracking kind of situations. So all these are being studied before it is actually implanted into a sample, okay, into a human being. So a lot of people have been working. Another type of implants are dental implants. Okay, particularly whenever your jaw is broken. See, one important thing about dental implants is that the type of implants that we use for dental applications are entirely different from what you use in a bone type of application or anything interior your body, because interior of your body the conditions are more or less the same throughout your kind of life, or in a particular day if you consider, it's more or less the same conditions, whereas in a dental conditions the conditions change almost every minute. Just after this class you go for a cup of tea, you take a hot tea, so immediately if you are crazy you go to ice cream parlor, you take a ice cream, let's say. So you see all kinds of, and also the type of food that we take. One day we take a very sour food, let's say, one day we take a very hot stuff. So all kinds of the pH conditions of the things, the temperature conditions of the food that we take keep changing very widely. So because of which the materials that we are going to use there should be compatible for all these conditions. So that's why people are very careful in choosing materials for dental applications. Particularly titanium based alloys are ideally suited for all these applications where they have excellent corrosion resistance under all extreme conditions of body conditions, under different pH levels people have tried, and seen that they are very good. So that is one of the major areas of titanium based alloys in addition to the aircraft. The basic starting point for titanium based alloys was the aircraft applications, where we have seen already where we use, and the recent applications are more on the biomedical applications, particularly dental implants or bone implants, or for example sensors where you need shape memory alloys. We will stop with this. Thank you very much.